In this video, we will be discussing multiple linear regression. So if simple linear regression only has one independent variable mapped to a dependent variable, multiple linear regression examines two or more independent variables in relationship to a single dependent variable. Therefore, the generalized linear model looks like this. Y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 through beta k times xk plus the error term, where k is the number of independent variables included in the model. So that error term comes with the same assumptions as in simple linear regression. We assume that it is a normally distributed random variable with an expected value of 0 and constant variance. Again, same as with simple linear regression, if these assumptions do not hold, your linear model is not valid. And we'll come back to how to check these assumptions in R in just a little bit. You can also calculate a correlation coefficient, rho, for multiple linear regression models. It measures the degree of linear relationships between the independent variables and the dependent variables. Again, this value is between -1 and 1, where the closer it is to 0, the smaller or the weaker the linear relationship. An absolute value of 1 means that there is a perfect correlation between the dependent variable and the independent variables. The value of R is, again, independent of which variable is the response and which are the predictor variables, and it's independent of units of measurements. So again, really good for comparing linear models to each other. And when you square this, you get the coefficient of determination, R squared, aptly named. And R squared is the percentage of variance in the dependent variable that the linear model can explain using the independent variables. Lastly, you can also do an ANOVA analysis or analysis of variance for multiple linear regression. This is very similar to doing an ANOVA for simple linear regression. The only thing that changes are the degrees of freedom here, where you take into account the number of independent variables k. So let's look at an example in R. For this example, we'll be using data from the ECDAT package, and the ECDAT package is really useful in that it contains several hundred data sets just for academic use and to kind of explore and hone your data analysis skills. So the data set we'll be using in this example is the California school data set, CA school. And so this is data from schools in California and just various statistics on those schools. So we'll be looking at the average test score. We're just going to assign all of our variables to actual R variables first, which will make our analysis that much easier to have these predefined. We're also going to look at the percentage of students who are on reduced lunches, the enrollment in the school, the total number of students enrolled in the school, and computers, the number of computers a school has. Okay, and then we'll put for this example, we'll use the average test score as our dependent variable, and we'll look at that in relation to the percentage of students who are on reduced lunch, reduced price lunch, excuse me. The number of students enrolled at the school and the number of computers the school has to see if any of these three variables has an effect on the average test score at a particular school. So we're going to put all of these variables that we're looking at into a separate data frame just to make things easier for each other, easier for ourselves. Again, using the data frame command. Okay. So now if we look at this data, we can see the average test score, the percentage of students on reduced lunch, the enrollment numbers, and the number of computers at the school. So let's plot this data just to see, do we think there's going to be a significant relationship between certain variables, or are there going to be any variables that are correlated within themselves? So looking at this, we can see that there is what looks to be a fairly negative linear correlation between the average test score and the percentage of students on reduced lunch. There's also some sort of correlation between enrollment and computers, although that seems to make sense as the number of computers in the school would probably go up as the number of students did. There doesn't seem to be a lot of a huge linear relationship between the average test score and enrollment, or average test score and the number of computers. But we'll see in our linear model if those are significant or not. Okay, so let's create that linear model again using, we'll call it fit, and we'll use the linear model or LM command. So our first input for this function is the dependent variable, the average test score, and then a tilde, not a hyphen, a tilde, to the independent variables, the reduced lunch plus the enrollment plus computers. And then we'll have to tell it where to look for this data, which we named school_data. Okay, so we can print a summary of this linear model using the summary command. And we can see that we get an intercept of 0.0068. You'll notice that here. Very small intercept. Again, most of these are very small coefficients. And they seem to be fairly significant. Our intercept is significant, which is normally not a great sign. Looking at our adjusted R² value, we're explaining about 75% of the variance in the average test score using the percentage of students on reduced lunches, enrollment, and computers variables. But according to the p-value, it does seem to be a significant model. So what's a really useful function, especially when you're doing multiple linear regression, is the step function. And so what this does is it takes either a completely full model or a completely empty model. And it runs through several internal tests. It is possible to do this by hand. Again, it's much easier in R. And it compares different models. So if you have 20 independent variables, it can quickly run through those and tell you which to include in your model for the most accurate linear relationship. So this is found in the mass package. And so we'll call this function fit.s for step. And then the step AIC. And so AIC is the criterion that it's comparing linear models with. There are different criterion. This is the one that R chooses to use. Fit is our initial full model, and we'll say that we want it to go in both directions. And what that means is that it's both going to add and remove variables to create the the best linear model You can do it forwards in terms of when a forward stepwise regression, it it starts with an empty linear model and adds variables as you go along to increase the percentage variance explained by the model. And in a backward stepwise regression, it does the opposite. It starts with a completely full model and takes away variables until you explain the most variance in the data. So this way, we're going to do both. We only have 3 independent variables, so we'll see if anything changes. It seems unlikely, but is also possible. Okay, so now we can print a summary of this model, fit.s, and see that pretty much nothing changed. It's more common to see a different model here when you have more independent variables in the data. But now that we know that our model that includes all 3 of the independent variables is the most accurate, we can check our assumptions again. So we'll divide our plot space up into 2, and we'll do a QQ norm plot. So this checks the assumption that the residuals, or the errors, are normally distributed. We can also add a QQ line to this plot. And you can see here that it is an exceptionally good fit, which strongly indicates that the residuals are normally distributed, which is what we want. There's a little bit of deviation at the tails. That's not unusual. For the most part, these fall right on that 45-degree line, indicating normality. We can also plot the residuals against the fitted model to check for constancy, the constant variance. So if we zoom in, we can see that the spread of these residuals does not really seem to change over time, which is good. They look like a shotgun blast, random, which is exactly what we want. If we were to see some sort of trend in this plot, it would indicate some sort of systematic error, and that would indicate that our model is not valid and that something else is going on. It may be a missing variable, it may be a non-random sample, etc., etc. So, and lastly, we can also do an ANOVA of this model. So again, that's the ANOVA command, and it just takes the linear model as an input. And you can see here it looks at the 3 different independent variables, and then tells you if they are significant at some levels. So you'll note here that the reduced lunch is, as we saw in the plot earlier, is highly significant, and there does seem to be a very strong linear relationship to the average test score. It's significant at a 0.001 level. The computers variable, the number of computers the school has, also seems to be fairly significant at a 0.05 level. However, the enrollment numbers are only significant at a 0.1 level. So depending on your cutoffs for your values, it may not be wise to include the enrollment variable in your model. But that is, again, based on your alpha level, your significance cutoff. However, we can see from this that there is some clear linear relationship between reduced lunch and computers and the average test score. So, more information on multiple linear regressions, ANOVAs, and model assumption checking can be found in your textbook, Probability and Statistics for Engineering and the Sciences by J. Devore.